Hello everyone. So in this pre-lecture tutorial, we are going to sort of expand our skill set a little bit. In the last pre-lecture tutorial, we were trying to figure out how to apply the law of mass action to a set of chemical reactions in order to write the equilibrium constant for each reaction. However, all of those reactions occurred all within the same state of matter. Okay? And so the procedure is a little bit different when we have chemical reactions that take place between reactants and products that are in different physical states. So for example, in this first chemical reaction that I have here on the slide, I have a reactant in the solid state, but my products are both aqueous solutions. And so we have to sort of account for that when we apply the law of mass action. And the way that we account for that is very simple. Whenever we construct an equilibrium constant expression, we only include those substances that are either aqueous solutions or gases. Pure solids and pure liquids are not included in equilibrium constant expressions. And so if I were to write Kc for this reaction, then I would go and I would write the concentration of my calcium cation times my concentration of my chloride ion squared, because again of the stoichiometric coefficient of 2 in front of the chloride ion. Normally, I would go and I would include the concentration of the reactant, but this reactant is in the solid state. And as I said, basically anything that's in the solid state, or anything that's a pure solid, I should say, or anything that's a pure liquid, would not be included in the equilibrium constant expression. And so I would not include it for this particular equilibrium constant. To sort of drive the point home, let's actually take a couple more examples. So for this second reaction, notice that I have 3 species that are in aqueous solution, but water in its pure liquid form. And so if I were going to write the equilibrium constant expression for this reaction, I would have my hydronium ion concentration multiplied by my acetate ion concentration and divide that through by my concentration of acetic acid. But in this case, I would not include the water since water is a pure liquid. And one more example. Okay, here I have magnesium oxide in its solid form reacting with carbon dioxide to give me magnesium carbonate. And so here, if you notice, the magnesium carbonate is in its solid state, and so is the magnesium oxide. And so I would go and I would begin to write the equilibrium constant expression by just putting a 1 in place of where the product concentrations would go, because there's only one product, but that product is a pure solid, and pure solids are not included in the equilibrium constant expression. And so it would just be 1 over, and in this case it would be the carbon dioxide concentration. Again, note that I would not include the magnesium oxide since that is also a pure solid. And this also applies if I were going to be constructing a Kp expression instead. So for example, here, if I were to write a Kp expression for this reaction, since it does involve a gas, then I could also say that Kp is 1 over the partial pressure of carbon dioxide as well. And again, note, I would not include the magnesium carbonate or the magnesium oxide. Now, as it turns out, when we calculate equilibrium constants, each of these quantities that are included in the equilibrium constant expression, they're meant to be equilibrium versions of those quantities. So these should be equilibrium concentrations for this Kp expression that we assembled for the last example reaction on the slide. This would be the partial pressure of carbon dioxide, again, at equilibrium. And if I use equilibrium concentrations or equilibrium partial pressures, then I will be calculating my equilibrium constant. However, it is not mathematically impossible to actually use concentrations or use partial pressures that occur within the reaction system when the reaction system is not at equilibrium. And so I can still calculate the ratio, but it will no longer be the equilibrium constant per se. It would be something called the reaction quotient. So basically the reaction quotient is actually the same ratio as the equilibrium constant, but evaluated for concentrations and pressures other than those at equilibrium. And so one might ask, well, why would I want to do that? Well, we would want to do that because, as it turns out, the reaction quotient is actually a pretty useful diagnostic tool. So, for example, I have this first problem, and in this first problem, I'm already told up front that I'm at 740 degrees Celsius, and the reaction system that I will be studying has an equilibrium constant of 0.006 for the decomposition of calcium carbonate. We're given the chemical equation for the decomposition reaction of calcium carbonate. They're asking us to find the reaction quotient and predict how the reaction will proceed if the carbon dioxide molar concentration is 0.004 molar. And so the first thing I should do is write an expression for the reaction quotient. And as I said, it's actually the same ratio as the equilibrium constant. So we would just simply apply the law of mass action as we have been doing. And so if you notice, the carbon dioxide is a gas, but every other species involved in this reaction is a pure solid. And so that would mean that my reaction quotient in this case is merely just the molar concentration of carbon dioxide. So that means that the reaction quotient is 0.0004. And the next thing I should do is compare that to my value of my equilibrium constant. As it turns out, my equilibrium constant is 0.0060. So Q, in this case, is less than K. And the way it works is equilibrium processes will want to actually change until Q equals K. And so in this case, since Q is smaller than K, the reaction is going to proceed in the direction that makes Q the same value as K. Q must get larger. And as we can see from the equilibrium constant or reaction quotient expression, it's only the carbon dioxide concentration that controls the value of Q and K. If Q must get larger, then that must mean that the reaction must proceed towards the product, so that the concentration of carbon dioxide will increase, and in so doing, cause the reaction quotient to increase until it equals the equilibrium constant. And so if that's the case, then that means the reaction must proceed towards the products. Okay, let's take one more example of that so you can see it in action again, and let's take an example that's a little bit more complex than just simply looking at one individual value. Let's actually put one together where we have to actually calculate something. In this case, in this second example, all right, I have an equilibrium constant for this reaction at 527 degrees Celsius, and that equilibrium constant is 5.10. I'm given concentrations of carbon monoxide, water, hydrogen, and carbon dioxide, and they're asking me to calculate Q. So that means that these concentrations may or may not be equilibrium concentrations. I'm just going to have to evaluate the reaction quotient and find out for myself. And so I would have to apply the law of mass action. So Q would equal, and if we look, every single reactant and product is a gas. And so that means everything should be included when we apply the law of mass action. So again, taking products over reactants, that would be my concentration of hydrogen, multiplied by my concentration of carbon dioxide, divided by my concentration of carbon monoxide, and my concentration of water vapor. And so if I go ahead and substitute in, my concentration of hydrogen is 0.42 molar. My concentration of carbon dioxide is 0.37 molar. I'm going to divide that through by my concentration of carbon monoxide, which is 0.15 molar, and my concentration of water vapor, which is 0.25 molar. And so I'm going to pull out my calculator, and I'm going to go ahead and do the math. And if I do that, I end up with a value of 4.14. So let's compare that to K. K was 5.10. So that means this is another example where Q is less than K. And so looking at Q and its expression, I see that it is a fraction, a ratio. And so, as I mentioned earlier, the reaction is going to try to change in such a way that Q will eventually equal K. And so since Q is less than K, that means that Q must get larger, as in the first example. The only way it's going to get larger is if the concentrations of my products increase, because then the numerator of this ratio will get larger, and then the value as a whole will get larger, hopefully until I get this target value of 5.10. And so once again, this must mean that this reaction will proceed towards the products. Okay, so to summarize, when I use the reaction quotient, if the reaction quotient is equal to the equilibrium constant, then that means that the reaction is at equilibrium. As we saw twice over in these examples, basically if Q is less than the equilibrium constant, then that means that Q must get larger, and if Q must get larger, then that means that the reaction proceeds towards the products. However, if I do my calculation of Q, and Q is greater than the equilibrium constant, then that means that Q must get smaller. And if Q has to get smaller, then that means that the reaction proceeds towards the reactants. Okay, or if I were looking at a reaction equation, if I'm proceeding towards the products, as in the second case here, then basically it would proceed from left to right as we typically write reaction equations. But if the third case is correct and Q must get smaller, then that means the reaction is actually going to proceed backwards from right to left in the direction opposite to what we wrote the reaction equation. And so go ahead and try the follow-up assignment. Again, if you have any further questions, email. We'll certainly discuss this in class together and take some additional examples. Okay? Have a good night.